ContiMap, Continuous Heatmap for Large Time Series Data by Phượng Phạm, Ngân Nguyễn and Thu Đặng. This picture shows the examples of ContiMap in visualizing CPU utilization. On the left is conventional Heatmap and on the right is the ContiMap. It is clear that the ContiMap approach is better at giving the overview of the data, and at the same time it is faster because we provide an approach for abstracting large number of time series data. It's helped to reduce the rendering time and get better overview of the data. We also provide heuristics for ordering a large number of time series with the trade-off between the visual quality and computation time. This picture shows different levels of data aggregations and visual abstractions for the popular faithful datasets. On the left, you see the original data. At the center, we use hexagon bins to bin the data and visualize them. It's clear that the visualization is easier and clearer to see the overviews of the data. Darker blue means higher density. On the right side, it's even higher level of aggregation and visual abstraction. We use contour polygons in order to represent the same data. So it needs fewer elements to visualize and still give good overviews of the data. So we have to do this because we have several constraints such as the large amounts of data to be visualized, limited human cognitive load, and limited display resolutions. Data aggregations and visual abstraction help to reduce rendering time and get better overviews. That's why we propose to use continuous heatmap for large time series data. So why do we use Heatmap? Because it's a common approach for visualizing large number of time series. It also helps to reveal the patterns and avoid cluttering issues. In this case, ordering the data items is important because it's critical for our approach to bring similar cells and form groups. It helps to generate larger display contour areas or the blobs, thus reduce display elements needed and help to reveal the patterns. For instance, we applied our ContiMap approach in visualizing CPU temperatures in our high-performance computing centers over here. So on top is the data visualized with conventional approach with a lots of number of cells. The second one is the ContiMap with random orders, or we don't have orders at all. And if we use the polygons areas to display, there are 422 blobs needed to display. It is smaller than this one. However, the visualization quality is still not as good. After outlining proper ordering of the data items by their similarity, we can reduce the number of the polygons areas needed to visualize this item to 154, and it shows a much better visualization. And also, we only need to use a fewer number of polygons to display this data. Therefore, ordering is important. However, ordering has the constraints that we only could order the vertical directions. The reason is the horizontal direction is constrained by the time. As orders of the items is important, but ordering items to find the best one is an NP-hard problem. Therefore, we offer a heuristic to reduce the complexity. The algorithm starts with order the n input time series by their average value, and we can use different types of values to do the order, such as the medians. However, we selected the average because it's helped to avoid the impacts of outliers in a large time series. The second step is for every entry I, we consider k of its neighbors only, because we assume that the average order helps already to bring similar items relatively close to one another. So we don't have to consider all the other cases, but only k of its neighbors. It helps to reduce the ordering suspects to k nearest neighbors only. Then for every entry ei, we find the similarity to its k neighbors using Euclidean distance in this case, but in other cases we can consider other kind of distance matrix like dynamic time warping. We select the neighbor ej for entry ei as the two should be the closest to one another, ei as the aj, and we go back to step number 3 and continue to find the next neighbor. We'll stop and return the orders list L when it contains all the time series. It consists of several components, and the first one is the pre-processing one with help the data cleaning, computing average values, and ordering of the time series based on their average values. The next one is ordering. We find the order of the items using the previously mentioned algorithms. Then rendering, we will bring proximity cells together and form the polygons. We also add interactions such as filtering and searching and fisheye on mouse over. So source code and the webpage demo of this ContiMap implementation is available in this link, and whenever possible, the computation tasks are divided and executed in parallel. Currently implemented in JavaScript, but could be developed in other programming languages. We also outline ContiMap in several use cases. Use case number 1, we applied it to Alibaba cluster trace dataset version number 2018, and we apply on CPU utilization percentage, the memory utilization percentage, and also this IO percentage. The x-axis contains 360 time steps. The y-axis represents 3,000 active machines at this time. If we use conventional approach, it's gonna require about 3.4 million cells to visualize the same information. If we use k-enables as 1,500 in this case to reduce this into 27,000 for the blobs for the first variable, 4,000 blobs for the second variable, and also about 14,000 blobs for the third variable. It helped to show that the CPU utilization is mostly below 40% with a few high points over here, and the memory utilization is mostly above 80%, and this IO is very idle. So if Alibaba needs to upgrade its cluster, the bottleneck is the memory usage, and it should first focus on memories. The second use case is we applied into high-performance computing centers, and the variables are CPU temperatures, fan speed, and power consumptions. The x-axis represents 721 time steps for one day, and the y-axis represents 467 computation nodes in this center. The visualization elements required, if we use individual cells, it's going to require about 1 million cells to visualize. And if we use the k equal to 466, then it's have to read it into 2,000, 0.7,000, and 2,900 blobs correspondingly. And this one, it's useful to reveal critical events in this one with large amount of data. For instance, we have the chill water incidents that we're going to be explaining. So this one have to highlight the events at one something, the temperatures of the computation node start to increase, and at about 2, the water temperatures begin to raise, and at about 15 to 4, this cluster is thrust, and at 4 they need to shut down the whole centers for a few hours, then they're gonna start again. So this one helps to monitor and indicates critical events and when it happens and why. We also apply into gene expression data. The dataset consists of 20,000 genes in 12 conditions. 6 of them are the control conditions and another 6 for treatment conditions. And the x-axis represents the 12 conditions, while the y-axis represents 20,000 genes. The abbreviation used in this case is listed here. The computation time, if we use the conventional approach, it's going to lead to page not responding because there are too many elements to be displayed. But if we use ContiMap, it can be visualized within a few minutes. It helps to highlight the highly expressed genes. Specifically, there are 175 upregulated genes, and this visualization again, the x-axis contains the 12 conditions, while the y-axis contains the highly expressed genes. The color ranging from low to high, as green to red. Then the observation is it's useful to highlight the highly expressed genes because you can see the large area of red over here, which means they are upregulated. We also applied our ContiMap into solar flare prediction case. Specifically, we applied to the fold 1 of this dataset with 76,000 of objects, and each object contained one varied time series for 25 variables. And the task is to make the predictions of whether there is a flare event or not. The x-axis represents 60 time steps, and the y-axis represents 1,000 randomly sampled objects. And this visualization helps us to get the overviews of the variables. It shows like the first 2 variables here are very important and will be selected for the classification task because they are different between the 2 classes. Meanwhile, this variable is not that important because there is no such big difference between the 2 classes for the same variable. It is interesting for the last case as well, even though they are different. However, they shouldn't be selected because this variable are different, but they are different in an inconsistent way. Some are decreasing while some others are increasing. So it's not gonna be helpful in classification task. As selecting the k number of neighbors is important, we also provide an evaluations for the users to know which k numbers to select. The dataset for testing is the Alibaba cluster trace, as mentioned. The y-axis in this case represent the active computers, while the x-axis represent 60 timestamps. It is observable from these pictures that when we increase the number of neighbors, the visual quality start to increase. At the same time, the ordering time start to increase sharply, and the rendering time will reduce because we have fewer blobs to render. However, at some point, even when we increase the number of neighbors, the visual quality will not increase much, while the ordering time will increase sharply. So you can see from here, the red one is the number of blobs, while the blue one represents time. So when we increase the number of neighbors, the ordering times increase sharply, while the number of blobs reduce slowly, and at some times it does not reduce anymore. So the rendering time is also reduced, but some time points it will not reduce anymore because number of blobs is not reducing. And we can also see that the rendering time for ContiMap approach is much lower than the rendering time for the conventional approach. Therefore, selecting the k in this case is important. Conclusions. This will provide an approach for extracting large number of time series data ASAP to reduce rendering time and give better overviews of the data. We offer a heuristic for ordering large number of time series with a trade-off between visual quality and computation time. We also provide implementation and the web page demo in this location. We apply it in various real-world datasets, and we provide evaluation to know the trade-off between selecting number of k neighbors, the visual quality, and the computation time. This one is a reference to several of the data sources that we described above. Thank you very much, and if you have any questions, you can address now or you can contact us. Thank you.